Okay, so pure substance is either a compound or an element. And so an example of an element could be something like iron. If somebody give me an example of a compound with iron in it. Say again? Steel, that's an alloy. It's actually a mixture. I don't know who just said steel. So it's a weird mix of actually of metals and carbon. Anything? Just give me another example of iron something. Iron what? That's close. Middle initial. Iron 3 oxide, something like that could work. So iron 3 oxide would be like that. So those are pure substances. They're compounds or elements. But then a mixture is a mixture or a blend of said elements or compounds or elements and compounds. So that would be a good example of an alloy. Steel is an alloy, and it's a combination of iron and carbon, but not a compound of iron and carbon because it's not chemically bound. It's still a blend. So there's a lot of other mixtures though, and we breathe one. What's in the air we breathe? Say again? O2, what else? Nitrogen, say again? Carbon dioxide, and anything else you can think of? Water vapor, say again? Argon is another component of that. It's actually still significant. Water vapor. So these are all blended together, but they're not chemically bound together. That's why they're a mixture and not a compound. All right, so what are you observing in a chemical change? There's actually 4 to 5 evidences of chemical change. I'll start with one. Gas evolution. Somebody tell me another. Heat evolution, or diminishing of heat, so it's temperature change. Color change can be indicative of a chemical change or a physical change. It kind of depends on how the color change is initiated. If you're making a new compound that just happens to have a different color, that's a chemical change. If you're just putting food dye in water, that's a physical change because you're actually making a mixture, which is a physical combination. So that was, what did we just say so far? Temperature change, gas evolution, color change. What else? When you put 2 liquids together and you make a solid? Say again, loud and proud. That's actually, so 2 liquids chemically combining together to make a new substance that is a solid. It's called a precipitate, PPT. Precipitate, and we'll deal with that a little bit more when we actually start our reactions next unit, more so. That's pretty good list. Anything else you guys can think of? So occasionally when the gas is made or the fumes are made, they'll have a scent, and that scent or odor would be indicative of a new substance if it wasn't there before. So I'll kind of keep that with gas evolution. Now, whenever these changes are happening, you're actually making a new substance. Maybe you can tell, maybe you can't tell from looking at it with your bare eyes, but you're making a new substance. However, in physical changes, you're not making a new substance. You're just making it look different. So what are some ways we can make a substance look different? Megan, give me one.
For physical changes.
Mm-hmm. So color change, that was expected, that you would know that you're making a mixture of something that was colored and maybe something that wasn't, so it would make a blend. CJ, give me something else. Can't be temperature change because that's indicative of a chemical reaction. So along with temperature change, generally we force something to happen. Thank you, Miriam. So physical state, like state, solid, liquid, gas. Gigi, give me something else. So melting, freezing, boiling, those are all the names that go along with when we're actually causing the physical change or the physical change of the state. Something else?
Change shape, like cut it.
Right, so you can tear something up, you can cut it, you can mold it into something new, someone could just change shape to encapsulate all those. Okay, that's a pretty good list. So when you're looking at, I think it was 49 in the textbook for the chapter questions, what were you looking at in those images to tell if it was physical or chemical? I heard molecules. Jillian, can you expand on that? If you're looking at, it was 49 in the textbook, how would you know just by looking at the pictures from before and after if it was a chemical change? Molecule? I'll put it together for you.
Yeah, it's like they are chemically bonded with new ones.
Okay, so new chemical composition. So if you change the composition of the structure, it has changed its chemical formula, therefore it was a chemical change. And then, William, we talked earlier, tell me about the physical change. What was something that you observed?
Physical change will, like, the molecules having grouped together when they had tablets, but they kept the same composition.
Right, so they kept the same chemical composition, but they rearranged the way they were oriented with each other, which just was probably like, I went from solid to liquid to gas or vice versa. So they spread out or they rotated around each other in different ways. Okay, this is a note to myself because I'm going to forget. I'm going to pass around this. I need to know when your birthdays are. So if you'll just put your name under the birthday month, I'll probably might have to do some group celebrations if we got a lot of people like in September. I'm going to start over here, put your name under the birthday month. And then other reminders for myself, summer package, number 7 requires you to utilize molarity. And we're not talking about molarity, so it's going to be in this unit. So make sure that you're omitting, you're not doing number 7 on the summer package. And I already took this one. Hey. I'm in first year right now, so they've already gone to first year. You're fine, me. Okay, and then eventually everybody will present a homework problem, right? So I have a list right here of the ones that I'd like to be presented as that homework assignment is made. So I'm gonna have you guys sign up, and I think there's only like maybe 10 spots here to sign up, so not everybody at once, but if you don't sign up for unit 1, you'll be signing up for unit 2. So for now, I'm just gonna put it right here, and we're not gonna sign up just yet, but you won't really know what the questions are, so you just get the luck of the draw. Some of them are harder than others, but I'm always there to help you through it. And then for today, after we review a little bit more of the math basics, I want to make sure I answer some of your lab questions, but I'm thinking as I go through lecture today with stoichiometry, it's going to be an Emma talks a lot day, I'm sorry, you'll answer some of your own questions that way. And if we can get to finishing up lab and homework, that would be great today. And get the nomenclature quiz tomorrow. And it's 27 nomenclature questions, 1 extra credit question, a good blend. Well, predominantly, let's be honest, what do we normally name a lot of? Ionics or covalents? Ionics, and they come in 2 varieties. Binary, which end in red, and then the ternary ones, which have a polyatomic ion in them, and they end generally in 8s or ites, right? So if you remember your 8s, naturally you will know your ites and your hypos and your pers if you know your 8s and your polys. And then there's a couple of acids in there as well, so know your acid nomenclature rules. Okay, I think that's all I need for now. Oh, last thing. These are all notes for myself. The NMSI, National Math and Science Institute, if you Google that and just put AP Chem, NMSI, they have fantastic little study guides. And I pulled this image from one of them, but I usually read them just to, get everything back in my brain before the school year begins. But there's one for every single topic. So like this one's chemical foundations and atoms, molecules, and ions. And it might be easier than reading the textbook. There's nice images and so forth, but I print them out for myself to take notes on. You guys could definitely just read them over in your, before you maybe take a test or before the unit. Okay, let's keep going. So I've got some diagrams over here, but first just making sure you understand the difference between accuracy and precision. Accuracy, if I'm shooting a basketball, what would be an accurate shot? Okay, in the goal, so swoosh, that would be accurate. For me to be precise, I would then need to say, okay, I'm going to hit the same spot over and over and over again. It's a reproducible result. But can I be precise without being accurate? Yes, because I can hit that right bank shot or that right side of the backboard over and over and over and over and over again, and I am super, super precise, but I would yet not be accurate because I'm not hitting the true value. So in these images here, I want you to go tell me which one's accurate. The diagram 1, 2, or 3? 3, definitely. We can see it's bullseye, right? But who's precise? 2 and 3. So 2 is precise but not accurate. 3 is accurate and precise because it's actually hitting the true value. Okay, so the 2 other types of error that we don't really talk about in honors chem, but we do need to just mention them here is because you can actually utilize this in your error analysis part of your lab, is that we have random error. Sometimes things just happen, and the random error does not have any kind of method to the madness. It can be here and here. There's not a directional error to it. So
So a scale could measure, 0.2 grams lower than it should, and they can again measure 0.2 grams higher than it should. And so you have an equal probability of that measurement being high or low. That's why it's called random. Systematic error, and I don't really use indeterminate or determinate, but you can say that word if you want to, I gotcha. But systematic error is when, like, maybe a scale is not calibrated very well, and it always measures 0.2 grams low. And so we have to calibrate it so that it doesn't have systematic error anymore. But we will notice that sometimes in our equipment. So systematic error will have the same directional error, so it would be too low or too high. So looking at these diagrams again, looking at 1 and 2, which of these has random error? Random error is number 1 because you've got the darts on the left and the right and up and down, so it's not systematic, it's a random error. But then the other one is a systematic error because every time that person was shooting up or right. That would be me and probably in darts and golf. So I'm no good, slicing them all the time. Okay, but I did get a PGA and I saw these cool people. My husband was very into that, and I was like, okay, we're out here in the sunshine, that's all I need. Okay, so looking at this, let me scroll up just a tad more. Looking at this, talk to the person next to you, take maybe less than a minute, and discuss what's happening here, okay? So check for accuracy. Student filled the graduate cylinder to 25 milliliter mark, delivered water from the burette, and then read the volume delivered. The following are the results of the 5 trials. Is the graduated cylinder accurate? You got a yes or no answer?
No.
Okay, I'm hearing a lot of no's. Okay, so it's not accurate because it's not what? Okay, so our graduate cylinder, we're going to the mark that says 25 milliliters. But truly, how much water am I delivering into that? 26 plus, okay? So it's not accurate. This should be saying 26 or 26 point something because the burette is actually very, very accurate. It has it's got multiple graduations, which actually gives you accuracy or precision to 2 decimals, which is why you have 2 sig figs or 2 extra decimals here. So this is indicative of a better instrument or a more accurate instrument. This is not, because we don't have as many decimal places. So from that, you now tell me what kind of error is here. So everybody's saying systematic because what? So they're all skewing the same direction, right? So these are what they are, but they're all skewing low, low, low by about a milliliter and a half. Okay, who's on my website at this point? All right, go to links. The links page. It's the. Let me pull this up real fast. I think it's the second link down. Nope, third. Graduated cylinder measurement with uncertainty. So when you click that, you should have a American Chemical Society kind of sponsored link here. You might not do all 10, but I want you to click on these and begin the quiz and then try to determine with the meniscus the number of sig figs that should be reported and then the uncertainty in measurement. So just take a couple minutes and play around with that. And if you need to write down something for yourself, especially about uncertainty in measurement, that's me looking here. Closer look if you put in a closer look. Does anybody have their $25? Okay. I'm going to pass out receipts from yesterday, and then I'll come collect them while you guys are practicing. Thank you guys for getting that done soon. So you guys are realizing the uncertainty
is supposed to be what? What's kind of the definition they gave you on the first part? Half the distance between the two graduations that are right next to each other. So if it's a 10 milliliter graduation, then the uncertainty would be plus or minus 5 milliliters because they had to kind of split the difference.
So let's go to every single little line is 10. So you divide that by 2. So each little line on the graph is 0.1. So you divide that by 1.5.
I'm still in year 121. Take another minute just to get the hang of that so you understand how uncertainty works. Did I get off any other fees or did I miss a fee? Okay. All right, take one more minute. I'm hoping that you just got the idea. Give me a thumbs up if you think you got the idea down. Okay, just give me a quick check.
You always estimate what's different. So if you know that it can be 65, but then like you estimate 1, so you could be like 65 on the same thing. So when you look at that,
So you understand the I just don't get the one.
If it's a square,
you always estimate 1 something.
okay, so, you know, 13 would be the 1 decimal point. But,
I get the segments, but I just don't get that starts with
okay, so the
the
value,
line.
the value of each segment is 1, then it's just half of that. So if this on a scale, if this was like 40, and this was 60, it's like half of it.
So each one is what, 40, 60,
Every 100, and if it's thrown by 10, then it would be 5.
so you just do whatever one line is worth and then divide by 2. Yes.
I thought too much.
Except for this one.
It would be 5. Because it goes by 5. Yeah, that's so we're making just between the two. Just think of this as a 1. You want see what the point
There's 10 lines in between my
Did you post the lines? Oh, did you with the
all they got is A.
the software? We all didn't know that by ourselves and send each other.
She said it would be like what she said we did across the street. She said the corner size.
Yeah, she said that was just my own.
Like gas laws and everything. That was my research. I like fell apart. I just want to space out reading a question. I'm like, what am I supposed to even do?
Alright guys, we're going to switch modes. So, close the laptop for now. We'll log off later. We're going to do some math, okay? And I also printed some of this on your lecture notes. So I think it's like the second or third page back in your big tree packet I printed for you. And this information is review. And I'm going to make sure that I'm hitting the highlights and making sure that you're bringing things back to life. But if I'm going over things and you're like, we know it, let me know, because I want to let you start where you need to start on your own. Specifically, we're going to talk about mole relationships in a reaction standpoint. We're going to go through percent yields, and we're going to do limiting reagents. Okay, so I'm going to bring up one example for each one. So if you were able to record me and I take them with some extra notes, that would be beneficial to you. So I think after I do one example or two examples, it'll come back to life in your brain there. So in terms of reaction stoichiometry, what we did yesterday in the lab, did you guys do reactions yesterday in the lab? No. Not a single one. You did no reactions. You were just practicing lab equipment use and measuring out pure substances. So yesterday in the lab when we were doing stoichiometry, it was just, we call it compositional stoichiometry because it's just relating mass to moles to atoms or particles. And then occasionally you did an internal mole ratio where you're looking inside of a compound. This mole ratio that we're speaking of today is now reaction stoichiometry, so we're talking about a reactions mole ratio. So we have ammonium, what? Ammonium dichromate yields, no, this is not an ion, this is a compound. Name it, first name, last name. No prefixes because this is not covalent. Chromium 3 oxide. So this is an ionic compound. It's got a chromium in it, so you need to look for its charge in the compound, making nitrogen gas and water. Okay, so in this case, is this balanced? I got 2 chromiums. I got 8 H's. What do I need over here? A 4. What else do I need? I got 2 nitrogens, so we're good here. We good? Because there's 7 oxygens, 3 plus 4 is 7. Okay,
So making sure you're looking back at balancing. So we know the 5 types of reactions. One of them, synthesis. Second one, decomposition. Third, single replacement. Fourth, double replacement. Fifth, combustion. Those are our 5 types of reactions. So what you should be able to just maybe start, because we're really going to be doing this for next unit, but look at this number 2. You should be able to tell me, I have a single reactant. What kind of reaction has to happen here? A decomposition. I can't do anything else. I can't do synthesis, single, double, or combustion because I have nothing else but one singleton reactant. So water in this case actually breaks down to hydrogen gas and oxygen gas, and that's what it decomposes to into its 2 individual elements. And these are diatomic. So if I want to balance this, I need a what? 2 in front of the water and the hydrogen. So 4 H's, 2 oxygens, 2 oxygens. We're good. And these would be gaseous at room temperature simply because of the nature of their diatomic compounds. And next one, we have a compound that's ionic reacting with another compound that's ionic. There's only so many things ionic things can do, because what happens when ionic substances go into water, they ionize. So what do you think 4 ions can do? They just double replace. They switch a single partner. So calcium is a plus charge, phosphate is a negative charge. We're going to make what? Calcium phosphate. PO4, what am I missing? 3 and 2. Okay, so calcium phosphate and what else? Sodium chloride, and that's a 1 and a 1. We're good. Balance that up. I'm gonna wait on that for a second. I don't want to have to erase. What do I want to put in front of the calcium? In front of what? This calcium is 3, so I need a 3 in front of the calcium chloride. That gives me how many chlorines? 6, so I need a 6 in front of sodium chloride, and then I've got 6 sodiums over here, so I need a 2 here, and then that also satisfies my phosphate 2. Okay. When you're looking at your polyatomics, if they don't change, they're the same, just call them a big happy family. You can balance it faster that way. Okay, this has 3 carbons in it and a couple of hydrogens. It's called a hydrocarbon, okay? And that's an organic substance. It's reacting with oxygen. What does it mean if you react with oxygen? What kind of reaction? Combustion. Every single time you have a combustion reaction, there will be oxygen present as a reactant, and if it's combusting with a hydrocarbon, it always makes what 2 products? Water and CO2. And that's simply because that's the most stable arrangement for carbon, hydrogen, and oxygen when they make 2 more products like this. This is what your car does. This is what your body does when it's doing aerobic respiration in your body too. So I've got, does anybody know the name of 3 carbon substance? I'm hoping people who learned a little bit of organic last year do. It's not methane. It's what? It's propane. Butane has 4 carbons, so it would be C4H10. So this is propane, and we will eventually get back into this right here. But regardless, let's go ahead and balance. In the case of balancing combustion reactions, save your oxygen for last because they come in there many places. So start with your carbons first. So I've got 3 here, so I need 3 over here. And then I've got 8 H's here, so I need what here? 4, and then let's count total oxygens on the product side first because that's where it becomes most complex. I have what? 10. So I have 10 oxygens. So then what do I need over here? A 5. So 5 times 2 is 10. That's 4. That's 6. That's 10. We're good. Okay? So in the case of the coefficients, why do we need these coefficients? Why do we need a balanced chemical equation to work with? Okay, so law of conservation of matter. Heard, what did you say? Anybody else? So if I want to make something, generally, like if I'm making dinner, what am I likely to be following? A recipe. This is the recipe to make reactants into a set of products. And so this is the recipe that works. This is the proven recipe that says that we follow the law, because we're not criminals. We're going to follow the law of conservation of matter or mass, and we're going to make sure the atoms are rearranged. Also, it gives us a comparison or a ratio, which we call, I don't know if I have it up here, mole ratio, which would say, okay, for every 2 waters, I can make 1 oxygen molecule. For every 3 calcium chlorides, I can make 1 calcium phosphate. So that's the ratio we'll then be using in our reaction stoichiometry. Does that ring a bell? Shake your heads or something? Okay.
So before I get back into the reaction study chemistry, we will work a little bit with percent composition. I think I printed up some of this for you as well, close to that same page. So I try to print out some of the stuff for you guys, especially if it's just got questions on it. Percent composition is just like any percent. It is a part over a whole, right? So a section or a segment of a compound over the total compound. But if we're talking about percent composition, it is always mass, percent mass. It's not percent moles. That's one thing that people have a misconception about. Occasionally, and very occasionally, we'll deal with mass, percent by volume, but that'll be like next year. So if you're trying to find the actual percent composition of a compound of a given element, it'll say, for example, I'll show you this example down here, but I could say, what's the percent potassium in potassium permanganate? We just look at the potassium, and then we would continue looking at the total compound and do a comparison. So we would take the mass of the given element over the mass of the compound times 100, and that would be our mass percent. So I've given you this example, this potassium dichromate, because I want you to practice your nomenclature. What is potassium dichromate, Margaret?
Okay.
There's a 2 there.
Yeah.
There's a what here? I hear a 7, and then this dichromate has a charge of -2, so there we go. Okay, I was just trying to get you guys there. Okay, so there's our potassium dichromate. And when I don't specify the element, you should do every single one. We're going to start with potassium first. So the percent potassium, how many potassiums are in there? 2. Okay, there's 2 potassiums, so that's the number of atoms of the element. What's the molar mass of potassium? Get your periodic table out. 39.10 grams, and that's of potassium. We're going to put that over the total of potassium dichromate. Guys, you add that up for yourself. I'm going to find my notes sometimes. Add that up in your calculator. Hoping it's 249 or 294.2. It's 294.2. That is the grams of potassium dichromate. Okay, so we are doing the portion over the total times 100. You guys are going to have to do that for me, and then tell me your percent potassium. You got me?
I got 26.5.
26. I got 0.58, so I'm going to write that first. And so sig figs always, comes into play. With percents, we can't always do them 100% accuracy, but because we don't really have any measurements. None of these are measurements. These are all given constants of the molar mass of these substances. So I'm just going to take this and record it to 1 decimal, 26.6%, because we would round that 8, or the 5 up because of the 8. Okay, so if I wanted to do for chromium, what would be the only thing different here? Right, actually, you're right. We would keep the 2 because there's 2 chromiums, and I put 52.00 right there for chromium. And if I were to do it for oxygen, instead I would put 7 and then 16 right there for oxygen. Thumbs up if you got this. Okay, percent composition is easy peasy. It's every percent you've ever done in your life. We have a lab, we'll likely start tomorrow, but we will be using Epsom salt, which is magnesium sulfate heptahydrate, and we'll calculate the mass percent of that later. Okay. But in the case of water being included, we do like to name that, especially related to its prefix of its number of waters. So what's 7 in terms of the prefix system? Hepta. So we'd say heptahydrate to indicate that it's hydrated. This whole ionic crystal is hydrated with water. Tell me the formula for copper 2 sulfate pentahydrate. Write it down first. Copper 2 sulfate pentahydrate. Copper 2 sulfate pentahydrate. Random name card. Carrington, you got me? It's okay. I'm good. I don't bite. Not yet.
C-U-S and then H.
copper, hold on, sulfate, sorry, copper 2 sulfate.
Or
Yep, the 2's cancel, good. 5 waters. Yep. So with the hydrate, we want to be like, you're hydrated, you've had a lot of water, so think of it being like an actual water molecule. And note to self, that dot there means do not multiply when you're putting your atomic masses all together. It's just saying I'm an embedded crystal, so you add each of the elements and then add the mass of 7 waters to this given sample. Same thing here. So we put a dot there to indicate that it's an embedded water molecule in the crystalline structure. So that's copper 2 sulfate pentahydrate. So the 2 from copper and the 2 from sulfate have reduced. Okay, I'll do one more like that. Lithium chlorate dihydrate. Lithium chlorate dihydrate. What you got, Darcy? Dihydrate. 2 waters, good. And that's 1 plus and a 1 minus, we're good. Okay, now we're going to get down to the stoichiometry side of things. We don't need to do that, we're good. Oh, this is just a disclaimer. We will just talk about empirical molecular formulas in a couple days, but anytime we're reducing, and I've said this already 3 times probably in this week, anytime we're reducing to the lowest possible ratios, we are writing empirical formulas, and we always do that for ionic substances, but we'll never, ever, 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 ever do that for a covalent molecule, because the molecule structure is how that molecule is arranged. So like glucose right here, C6H12O6 is the molecular formula, and that's the formula of glucose. Like we would never want to reduce that. But if I ask just to say, this is the molecular formula, what is the empirical formula of that? We would then write down the empirical as the reduced form, which is what? CH2O, because there's a 1 and 1 here, because it's a 1 to 2 to 1 ratio, just like up to there. So there, in that case, we reduce them all by dividing by what? 6. Okay, so that's the disclaimer. We will go over that later. Quickly tell me the mole relationships, because you guys did a lot of these yesterday, and this will give you a chance to see just what you know and then add on to that. So we have a mole, and the mole is related to 1, 2, 3 things. First one, particles. And particles, that conversion is what number? And that's going to be number of particles per 1 mole. Okay? And then we have our mass. And the mass is different for every substance known to man. But where do we get the information for that? Periodic table. And these are PTOE, periodic table of elements. These are double-headed arrows. You can go both ways with this with your stoichiometry. The mole will also relate to volume, and that's of a gas at STP, standard temperature and pressure. And that relationship number is what? 22.4. Then we have the idea of the internal mole ratio, and I'm just going to do like a little re-loop. And that internal mole ratio is you looking back on itself to say how many of that atom do I have inside of my molecule or inside of my formula. And then we have the other idea, and I wish I'd drawn that way some. Hold on. Okie dokie. Then we have a relationship between a reactant or product and product, or reactant and product. And that would be 1 mole, I'm just going to put a reactant, versus mole of product. And that relationship within a reaction is called our molar ratio. And where would I get the molar ratio? From the coefficients of the balanced chemical equation. So the coefficients are our mole ratio within that balanced chemical equation, which we would say like 1 mole of water needs 2 moles of oxygen or something like that. And I could replicate all this on this side over here, but I'm not going to do that because it's the same exact thing. That's your mole map that you've worked with for a semester of your life. Okay, so I think that as we go on, you'll understand how to get from mole to mole or mole to mass and so forth between these different compounds, but it would be best to do it with application of a reaction. So go ahead, guys, and read the first question, and let's write down the reaction for that. As you're reading, just pull out the reactions first. And I'll print this for you. Right, Will? It's right there. Under reactions, or under what?
So I tried to print the questions for you. If you guys label your work well, please don't rewrite the question. We don't have time for that.
So we see the two reactants are what, Marcus? What are the two reactants in example 1?
Potassium iodide.
So the formula for the potassium iodide is what?
Yeah.
Okay, so potassium iodide and
PB.
NO3. Continue, a little bit more here.
And then there should be a potassium iodide.
Good, okay, so the two reactants in this case, potassium iodide and lead-2 nitrate, they're reacting. Before I even read further in this question, I want to know what this whole reaction is. Okay, so take a minute or 10 seconds, go ahead and do that for yourself, and then we'll proceed.
I'm gonna try to keep calling on different people. I tend to gravitate to who the names I know, so I'm working with you guys.
Lee, what you got for your products here? Okay, so lead-2 iodide and KNO3, so potassium nitrate. And then everybody balance, what do I need here? 2 in front of the potassium iodide and 2 in front of the potassium nitrate. Does that work? Yeah, we're good here. Okay, so I know you've read the question, but let's go ahead and analyze this together. What mass of potassium iodide is necessary to completely react with 20.61 grams of lead-2 nitrate as a double replacement reaction? Okay, so the way I've always taught it to my students, the way I learned it, and the way I've been successful with it is to write down what my givens and my unknowns are. So my question here is grams of potassium iodide, mass potassium iodide, okay? I know that's what I'm going to at the end. My starting point is the only other given here, which is the 20.61 grams of lead-2 nitrate. So my given, and you don't have to label it as given. My teacher used to make us label it as given. He's a great man, and I loved him, and he was my teacher for 3 years. 3 years. Physical science, yeah, I took physical science. Honors chemistry and AP chemistry for a full year. And then I had to go to college. Gosh, okay. So he made us write like that. But that's your given, that's your unknown. Before we start, let's just walk through the process in our head just to map out where we're going. You guys know we can't do crap with grams. You got to start with grams to get to what? Moles. So we're going to the moles of lead-2 nitrate using a smaller mass. Then we're going to get from moles of lead-2 nitrate to moles of potassium iodide because we want to get from A to B, from potassium, from lead-2 nitrate to potassium iodide. So how are we going to get from moles to moles? Do the mole ratio, which are coming from these coefficients 1 and 2. And then to finalize and get to grams of potassium iodide, you will do what? Use molar mass using the molar mass of the Ki, not the 2 there. Okay. I'm going to write it like, I'll do a couple, I've seen you guys do the fence post and then the what method I do, which is over the X's. I'll try to fence post for this one for a couple people to have something familiar for themselves. So 20.61 lead-2 nitrate. You guys are calculating molar masses for me, okay? So there's our grams of lead-2 nitrate. The grams need to cancel, grams need to go on bottom. So what is the molar mass of lead-2 nitrate? I'll give you guys a second there. Shock out and get there. Thank you, Julian. 1.2, something like that. Okay. Some of you guys will have more decimals based on which periodic table you're using, but this will be an approximate for most everybody. Okay, so I've successfully gotten from grams, canceled grams, gotten to moles of lead-2 nitrate. Everybody, what's the next step? What goes on top? 2 moles of potassium iodide because of this 2 coefficient right here. Comparing that to what I have of the lead-2 nitrate, which would be 1 mole. Why am I putting 1 mole of lead-2 nitrate on the bottom? So that it will cancel. So far I've canceled lead-2 nitrate grams, lead-2 nitrate grams, moles of lead-2 nitrate, moles of lead-2 nitrate. Now I've got to handle this mole of potassium iodide. And, oops, my X there. 1 mole on the bottom of potassium iodide is what? What molar mass? Thanks, guys. 166.01 grams of potassium iodide. Okay, and we have made it to our final destination. I always like to go back and double check that my unknown or my question was what I meant over here. and the lead 2 nitrate, potassium iodide moles have been canceled. The only unit I have left remaining is the question that was asked. So throw that in your calculator. 20.66 grams of potassium iodide. Okay, so why 20.66? Why did I not truncate this to something smaller? Right, so the initial measurement, which I started with, had 4 sig figs, and so everything past that is not technically a measurement. It is a process of realizing it's a constant in the periodic table, and then we take that and utilize the 4 sig figs here. Okay, thumbs up if that one makes sense. This is a normal reaction stoichiometry. It is not a limiting reagent. It didn't even have % yield and so forth in it. Okay. I need to do this one because of the percent. This is a slightly different question, and I want to show you how percent can be used as a conversion factor. So same reaction. Okay, so lead 2, I'm going to write this again just because I don't have it in front of my face. Or lead iodide plus PbO3. You guys write down your given and unknown if you don't mind. Okay, so in this case, this is a solution. So the solution is weird because just like you have sweet tea, part of it is sugar and tea and part of it is water. Well, the total solution is the sweet tea. So we have to think of that similarly. If we have a solution that's 22.5% potassium iodide, that statement means this. And this might be something helpful to write down like very explicitly so you understand how to do this in the future. So if it's 22.5% potassium iodide solution, that means that you have, in this case, 22.5 grams of potassium iodide, and I'll just put pure there so you understand that's different. That's the pure substance of potassium iodide for every, what if it's a percent? 100 grams of what? Of the whole solution, because the water's mixed with the potassium iodide. So I'll just put Ki solution. So if you have a percent, that's the part over the total, just like we had earlier, part over whole. So that can be used as a conversion factor. If you want to use it as a conversion factor, you may flip it if you need to, like because sometimes you need the solution on top, sometimes you need the pure item on top. So we're going to use that now to solve this problem. What is your starting point? Right, so this is our given, that's our starting point to start the process of stoichiometry. So 0.28 grams of lead 2 iodide has been precipitated. Can't do crap with grams, guys. What I gotta go to? Go to moles of what? So 1 mole of lead 2 iodide, molar mass. Shout it out when you get there. 461.0 grams of lead 2 iodide. Good. And I like to give you guys a chance to do the molar masses because you need to get used to looking at the periodic table again to realize where things are and you become just more efficient. Okay, so we have our grams canceling with grams, moles of lead 2 iodide remain. Next, remember, where are we going? I did not write on the question. Where are we going here? Yeah, so the real important part is that you're saying grams of the solution, so you understand that it's not just that, it's this, grams of potassium iodide solution. So I got to get to potassium iodide first, because I can't go straight to solution. So lead 2 iodide and potassium iodide relate how? Potassium iodide and, lead 2 iodide and potassium iodide is 2 to 1, right? So what goes on top? Say again? 2 moles of what? Potassium iodide go on top, what goes on bottom? 1 mole of lead 2 iodide. And that's because I want to cancel my moles of lead 2 iodide. Now I'm in moles of potassium iodide. I still can't use this conversion factor because I still don't have what? Grams, because this has grams in it. So now I need to do what? Convert from moles of lead, potassium iodide to grams of potassium iodide. So it goes on bottom. 1 mole, and every time you're doing molar mass, you always compare that mass to 1 mole of itself. And that is, I think we already did that, 166.0. We did that in our last problem. So before I continue, just verifying our grams of lead 2 iodide, cancel. Our moles of lead 2 iodide, cancel. Our moles of potassium iodide, cancel. I've got grams of potassium iodide pure. What's my last step? Christian?
Use the conversion.
So do I want to put it down just like it is here? Why do I want to flip it?
Because you want to get to the solution.
Right, I want the solution grams on top. So that's for the 100 grams of Ki solution. For that 100 grams, only 22.5% of that was pure, which is 22.5 grams. And that allows for that little annotation of solution makes me know I'm to the solution, not the pure, so it's helpful to write that. And your grams of Ki will cancel. And you guys calculate that one. We need a calculator borrow. I've got some. Oh, right. And no promises. Oh, yeah, it's got batteries. Come and grab this real fast. I've had lots of students leave their calculators and they never come back. And they don't have names on them, so I live the good life. I got like 10 extra calculators, guys. Don't leave your calculator. I'm trying to see if they've got batteries, that's all. I do have extra batteries, though. Who else needs one? Can you come grab me? Anybody else? Okay, answer. Good. Can you tell me that prior to rounding point 2-ish, something like that? Ki solution. So that's our kind of full answer. When we're going back to sig figs, we'll notice that we got 22.5%, which we can kind of count as 3 sig figs here, but in this case, our lowest sig fig rules the roost. So that's our 2 sig fig initial from our measurement. So this would be taking the 2 sig figs I have here, 8 and 9. However, because the 6 is after the 9, I have to allow it to round up, which then means I'm going to be at 0.90 grams of solution. Right, so that one just used a percent. Nothing different than normal. Just understanding percent can be used as a conversion factor. Thumbs up if you get that main point. I like to do my surveys, and thank you for participating. Okay. Okay, so we're doing percent yield and limiting reagent for the last bit here. This is a lot of text on the screen, but in the case of what you need to know, theoretical yield. In La La Land, if I theoretically could make exactly the amount of product that I should be able to make, I would be a perfect chemist. But the thing is, we have a lot of error that just naturally happens in the lab, you know, air pressure differences, impure substances, things like that. So it's the amount of product that should be made from initial reactants. We like to know that theoretical yield because it allows us to see how good our process was, how effective our process was when we were doing the experiment ourselves. So what do I compare that theoretical yield to? I compare it to the actual yield that I for real got in the lab. So if I had 10 grams of theoretical yield, I would get, by the way, the value is achieved by Stoich. Like, you have to calculate your theoretical yield by doing stoichiometry, because there's no way to do it in the lab. It's what we should get, which we would do by calculations. The actual yield is what I'm collecting myself in the lab. I'm not calculating it, it's going to be what I collected. Now, we're not going to get up in the middle of class right now and go do a lab real fast just so we can do a problem with this. So how would I probably give you in a problem the actual yield? Any takers? I just have to tell you, this is the yield, or this is how much Margaret collected in the lab. Like, I would have to say that as a phrase, so-and-so collected this in the lab. So it's what's actually produced, and many times we'll use the word collected, blah, 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 in the lab to say that's how it was, that was the actual yield of that particular experiment. So the comparison between the theoretical yield and actual yield gives us our percent yield to say how effective our process was. So actual yield over theoretical yield times 100 is what we calculate in order to find percent yield. So again, if we're doing actual yield and we're not perfect human beings, do you think our actual yield or our theoretical yield would be lower? Actual yield. We probably have a lower number here simply because we're going to lose some mass, we're going to have some, maybe scrape the evaporation dish all the way and so forth. This theoretically should be a higher number because it's going to be a pure, okay, 100% transfer. So most of the time our percent yields are going to be between 0 and 100. No one's probably going to get 100. And if you get over 100, what can you assume? You're wrong, okay, thanks. And you're probably made a mistake, like you didn't dehydrate it all the way, and there's still water crystals left over in your sample, and so there's contaminants there. So it's not going to be over 100. And if it's over 100%, then you've done something wrong. And that's where you would explain error in that case. We just accept our defeat, and then we explain our error, and then we move on. We don't cry about error. Error is good. Okay, so in the case of a limiting reagent situation, a particular reactant and another reactant will react. Well, I can have more of one reactant than the other. And if I have more than one of the other, one of them is going to run out first. If I run out of something first, that's going to control how much end product I can make. So it's the reactant that limits the amount of product that can be made. Everything else that's left over from the original reactant, we call the excess reagent or excess reactant. And that's the case where, I mean, if I got something left over, it's probably mixing with some other things and now it's contaminated. Would I want like an expensive reagent to be the excess, or would I want a more cheaply made reagent to be the excess? A cheap one, because it's going to probably be washed on the drain, or it's going to be thrown away with the rest of the contaminated waste. So in this example, peanut butter and jelly. I don't know if you were in my class, I had you make a peanut butter and jelly sandwich in my class, like on paper. But if I had 4 pieces of bread, okay, 4 bread, and 3 slices of peanut butter, PUD, yeah, 3 slices, you heard me, and 4 slices of jelly, assuming the recipe is 2 pieces of bread, 1 slice of peanut butter, and 1 slice of jelly for each of your sandwiches, here's my limiting reagent. The bread, I can make how many sandwiches with this? I can make 2 sandwiches. And that's because you know the ratio, you know how this is made. How many will this one make? Technically, you can make 3 sandwiches. And then how many will the jellies make? 4. So because you can do this very quickly, you can immediately see that this is the limiting reagent where these 2 are the excesses. And then you got mixed peanut butter and jelly, which isn't bad, but this would be limiting, you only get 2. Because we don't always want to do making final product, stoichiometry for everything, we actually do a comparison between the reactants to figure out who's going to run out first. So I'm going to show you something new. This is a process that actually is faster than the way we did it in Honors Chem. I think I just skipped something. And that process, I didn't. That process is going to be how I expect that you'll do limiting reagent probably from here on out, because it's going to be simpler in your head. Okay, so work with me here. This is called, the way I'm going to process this is called a BDA, or before, during, after. Before, during, and after table. And BDA is how I refer to that. Because when we talk about an experiment, I always have reactants before the reaction begins. What do I have after the reaction ends? Same. Products, and if the limiting reagent problem, an excess reagent. So I want to know how that change occurred. So if I was utilizing this example over here, and I made sandwiches, I would say, okay, I had 4 slices of bread. During the reaction, 4 slices of bread were consumed or utilized, and there was 0 left over. So that's what we're thinking about. How does the change occur over the course of the reaction? Okay, I'm going to do this one in a second, because this is my percent yield one. I'll go back to that in a second. This is my limiting reagent one. Okay, so go ahead, and this example 4 is in your packet. I'll go back to the percent yield. Write down your reaction first, and I'll write down the steps over here on the board if that's helpful. Write down your reaction first. And as you're writing that, somebody tell me what kind of reaction this is. Synthesis, right? So zinc and sulfur come together to make what? Zinc sulfide. What's the charge of zinc always? Do you have to tell me that in the, I'm sorry, if you were writing it, would you have to tell me that explicitly? No, you're assuming I know it. So step 1, balance chemical equation. Step 2, get 2 moles. And I'm going to show you how to organize this so it makes sense whenever I'm talking about it too. All right, so zinc, and space this out a little bit. You maybe already started writing, but space it out. Zinc plus sulfur yields zinc sulfide. I'm spacing out so I can have enough room to write what I need to write. Okay, so before the reaction begins, just going to segment these into sections so you see the layout. Before the reaction begins, I have how much of zinc? 25 grams. And I have 30 grams of sulfur. And I have how much product? 0. So I don't have any product, right? I have nothing. Okay, and I'm going to now ask for you to verify this is balanced. Check. This is a 1-to-1 ratio. This is an easy one. And I want you to take each of these to moles. Okay, so I know this is 0 moles. I got you there. But what's the molar mass of zinc? 63.59, something like that. 65.39. Okay, so 1 mole of zinc is 65.39 grams. Convert that to moles for me. I'm squeezing in this box. So 0.32. And put mole on it, so you're labeling all your units, everything, because this isn't just simply math, this is chemistry. All right, sulfur. 1 mole of sulfur is 32.06 grams. Convert that to moles. Any takers? 0.936, thank you. Okay, so in honors chem, the way you learn limiting reagent was you found your chemical equation and then you found how much you have of each reactant. Do you remember that terminology? Some of you, maybe, some of you guys who didn't have somebody here, I don't know, so work with me here. But this is what you have of both before the reaction begins. So if you want to put have right there for yourself, that might be just an indicator that you remember what you're doing here. So in honors chem, I made you take the zinc and compare it to the sulfur and do a mole ratio to figure out who's gonna, how much you needed, and then do a comparison between have and need and figure out who's gonna run out first. In AP, we do this in our head because basically this ratio allows us to go ahead and utilize the recipe in a more advanced way. You can take the moles that you have and divide it by its own coefficient. The moles you have and divide it by its own coefficient. And of course, these are 1, so this one's an easy one. Because when you divide it by its own coefficient, you get them to the same playing field, so you can then compare the moles you have of both. So that you can actually say, if I have a lower number of moles, I'm going to limit the reaction. So in this case, that divided by 1 is that, and that divided by 1 is that. So in your head, and I'll write down this stuff over here, you did what? Got the moles, and you did what? Divided by its own coefficient. And then what your conclusion of this is the limiting reagent is the smaller of the moles. And it's because you allowed for them to be compared at that point by dividing by their own coefficients. All right, so who's the limiting reagent in this case? Zinc. I'm going to put LR up here so you remember that's the limiting reagent, so that by default means sulfur is the excess reagent. Excess, like excess. Okay, so now let's let the reaction begin. Let's let it start. We know zinc and sulfur have to react. As zinc reacts, all of this mole, this amount it has, is going to be exhausted. It's going to be gone because it's limiting reagent. So during the reaction, I'm going to put a line here just to segment this for clarity. During the reaction, how much of that gets gone? All of it. So how would you show that to me? You would subtract 0.382 moles of itself, because every bit of it will be eliminated, it'll be consumed, it'll be used. Now, because it reacts in a 1-to-1 ratio, you have to indicate that under the sulfur. I can't say all the sulfur reacts because it all doesn't, but how would I know how much reacts? What you do is you say, okay, it reacts in a 1-to-1 mole ratio. So I'm going to react by subtracting 0.382 moles, and I'm going to label this just so you are very clear on what I'm doing here, but it's actually 0.382 moles of zinc reacting with sulfur in a 1 mole of sulfur to 1 mole of zinc ratio. So what I'm showing right here is that I've taken the moles of zinc and I've calculated how much sulfur would be also reacted. So that's a 1-to-1 ratio, so it's really easy. It's the same amount of sulfur. And that makes sense because you can see the 1-to-1 ratio here. Not every time am I going to write moles of sulfur over moles of zinc. And I'll elaborate there, but it's just you put the one that's the coefficient that's with this one on top, and and the coefficient with the LR on the bottom every single time you utilize this. Okay, I'm going to keep going, and then I'll take questions. Okay, so as these two react, I'm making what? I'm making zinc sulfide. I'm making products. So I subtracted over here, but what do you think I'm going to do over here? Add. So I'm adding, still using the limiting reagents moles, because that's what's basically controlling the entire problem, 0.382 moles of zinc in a what to what ratio? 1 to 1 again. So that's 1 mole of zinc sulfide over 1 mole of zinc. And I'll label that here, but this is too much detail to be put in these little boxes, because a lot of this becomes the process that you're just looking for your final product. Okay, so that's what's happening during the reaction. Zinc disappears, a little bit of sulfur reacts, and then there is product made. So after the reaction, how much do I have of everything left? Do your subtraction. That minus that is 0 moles. That minus that is, what is it? 554 moles of sulfur. And then this is the same 0.382 moles of zinc sulfide. It's just the subtraction problem. So if you're thinking back to have need, the beginning where it says before is a have, how much you're reacting during the reaction is your need, and then what's left over is excess or product. So in this case, I didn't even read the problem, I just started it. What was our question? Grams of zinc sulfide could be produced, right? And I give you one question here. Many times I'll give you 4. It'll be like, who's limiting reagent? Check. How much of excess is left over? We could take this as our excess, convert it to grams if we wanted to, and it'll say how much product is made. So we got our moles, let's convert this to grams. 1 mole of zinc sulfide is thank you. 97.45 maybe, and that would give us 32 or 37.2 grams of zinc sulfide. So that's the answer to this question. But what I'm showing you is a process that can answer many things at the same time. So the second question is related to like what I was just saying. I can ask you a question about the excess remaining, which would be here, taking our sulfur and then just converting it to what? Grams. So it says how many grams of excess reactant remain. I could take the moles of sulfur in grams. Okay. I don't know if you got the process in one question. I'm doing another one. Okay, and I want you to help me lead you as we go through it. Are you ready? Okay. Oh, I'm gonna skip that for a second. Okay. Start writing your balanced chemical equation now. I'll fill this out while you guys start. You may know what kind of reaction that is. Sigma replacement. So aluminum metal replaces chromium metal to make what? Aluminum oxide and chromium all out by itself. It got booted out of that relationship over there. And then so far so good. And now you're setting up your BDA box before. What do you have here before? I don't know. I'm not going to do the boxes this time. You guys can still make a table if you want to, but I'm just going to track it. 38 grams and 9 grams. And then what do I have over here? 0 and 0. I see people mouthing it to me. Don't be scared. It's not scary. We're just working together. So We can't do anything with grams. Everything always has to be in moles when you're doing a BDA chart. So you guys don't have to show me that molar mass conversion right here. If you can just convert that in your calculator and put the moles underneath it, I got you. Because that's becoming, you know, I showed a lot of work in the first one to give you every thought in my head, but I want you to know that you can do that. So that's 152 grams molar mass of chromium oxide. So that is 0.25 moles of chromium oxide. Chromium 3 oxide, sorry. Give me a thumbs up if that's what you got. Okay. And then molar mass of aluminum is 26.98. Yeah, 26.98. Convert that to moles, that'd be 0.3335. Yes, I'm extending that because I want to make sure I'm not rounding too soon. 0.3335 moles. I don't want to round too soon because it can cause error later on. And I have 0 moles here and 0 moles here. Okay, let's right now go through the whole process. We got our BC, we got our moles. Let's figure out who the limiting reagent is. So what do you guys do in your head? Dividing by its own coefficient. So 0.25 divided by 1, 0.25. 0.3335 divided by 2, doesn't matter. Is it less or more? It's less. So who's the limiting reagent? Aluminum is the limiting reagent. If you have lesser moles, when you put them to the same playing field with the coefficient conversion, I'll say, that is your limiting reagent. It's a very fast step, and then you begin your problem. All right, so now that you know your limiting reagent, what was the next thing you needed to do? Subtract it from the two reactants and adding it to the two products here. So we now need to use these coefficients very carefully. So during the reaction, 0.25 moles of chromium 3, let's go to the actual limiting reagent over here. So subtract 0.3335 moles of aluminum from itself. That's going to give us 0. That's the purpose of the limiting reagent. I'm going to use that same number though. The limiting reagent controls the groups here. Subtracting 0.3335, but with what ratio here? 1/2, because it's 1 mole of chromium oxide that reacts with every 2 aluminums. So if you're noting that for yourself, you'd say for the mole ratio, who always goes in the bottom? What coefficient? The coefficient of the limiting reagent is in denominator. Okay, so that's because basically what I'm doing is I'm converting the moles of the limiting reagent to the amount of that chromium 3 oxide that would be reacting with it. That's what I'm doing right here. So that's 3 moles. Okay, and then over here, I'm adding same number, 0.3335 moles of aluminum, but in a what ratio? 1/2 again, because this one is referring to aluminum oxide, and this 2 is referring to aluminum. Okay, and then same thing, next one, I'm adding 0.3335 moles in a what ratio? 2:2. This first 2 is chromium, and this second 2 is aluminum for the limiting reagent. So I'm doing a whole table because I haven't read the question yet, but it's because I want you to know how you can flush it out, or you can just do selected parts of it to answer the question given. All right, so what should be left of aluminum? 0. How much of this is left? You guys do the math. Say again, point. Okay, and then this is the same. Nope. How much is this? Is 0.16675, and this is 0.3335 moles. Once you get to that part, this is the easy. I mean, once you get past this part, everything else is easy because it's normal. You just have your moles, and you would convert it to grams or so forth. Yeah.
For the moles of chromium 3 oxide,
Mhm.
I got 0.0825.
This one? Oh, I maybe just didn't hear somebody. My bad. It'd be loud. I'm old. Yeah.
Can you go over it? Like, why is the 0.335 times 1/2 different than 0.33?
So this one I subtracted from 0.25. So did 0.25 moles minus whatever that is. Can you get this? Are you asking why that's different from this one? And that's because this is 0. And since I'm during the reaction, I'm consuming reactants and I'm producing products. Here I'm subtracting what I had originally, how much reacted and how much is remaining. But here I had 0 product, but as I produce product, I'm adding in relationship to the LR how much I can make. So yeah, that's a good point to differentiate between the left and right side here. All right, so let's read the question. So we don't have a lot of time left. I think we got like 9:05 again. Okay, so we got 15.2 grams of chromium metal that were collected. What does that mean? So you're seeing this right here, and you're saying this is what? Actual yield. Okay. Were collected along with an unmeasured amount of aluminum oxide. What was the percent yield for this experiment? Noticing that this is in grams of chromium metal. This right here is in moles. I can't compare them. That's apples and oranges. What I got to do this first? Right. So let's convert that to grams. So that's 1 mole of chromium is 52.00 grams. What is that? Can you guys calculate?
17.34.
Thank you. So that's 17.34 grams of chromium. Theoretically, if I made exactly what I need to make, that's theoretically how much I would make. And like I said, theoretically yield is calculated via stoichiometry. If the actual yield was 15.2, how do I do percent yield? Actual yield over theoretical yield times 100. So that's 15.2 grams of chromium divided by 17.34 grams of chromium times 100, and what percentage of? 87.6. I would totally have them on my lab. That's pretty good. It's not 50% yield, right? That's a pretty good yield. So what you're guessing is that if higher yield would be better. All right, I'm going to pause. Who feels like they understand this process a little bit better after the second one? All right. I'm feeling like you guys are okay if you can master, if you take a picture of this, if you didn't write it down. But in terms of homework, here's what I want. Look at 68, 67, 69 on your packet. It's like right under the problems you've been doing. I believe it says more reaction factors for more reaction factors. Yeah. 86, 87, 89. Again, on the top. So 86, 87, 89. I want you guys to do those, okay? The other ones that I have in the textbook, they're repetitive, they're similar, they actually utilize some of those diagrams again. So what I'll do is I'll leave these optional. The only one I want you to do is 47 from the textbook. So you have 4 problems, 86, 87, 89, and then problems number 47 on textbook page 187. So it's 4 stoichiometry, pretty heavy stoichiometry questions, which should be enough. You don't need more. My expectation is that you can continue on the lab where you can, but because I've spent a lot more time up here than I thought I would, I can try to work on it for tomorrow. Sometimes I have to push labs to different places because you get that as you go. I'd rather make sure you get the content you need so you're not freezing. Okay? So we leave in a minute. Will you guys put your log off your laptops and put this back? Sorry about that time. Yeah. Yes. So yes, you will have a periodic table, but you will not have your polyatomic ions, okay? Those are up here in the bank. And you guys can stop by and see me if you need to quickly after school. I have to go probably around 2:40 today, so if you guys need to stop in. I did see a lot of you yesterday, which I so appreciate getting those questions answered. Thanks. Thank you for your laptops up before you go. I'll put this video up now. I'll put this video up on YouTube very soon.